Hello everyone. Okay, so let's do this last problem. This is a long one, so make sure you write everything down. Okay, so let's calculate the pressure. We might need more space actually. So let's calculate the pressure of 1 mole of oxygen gas at 0 degrees Celsius in 1 liter, 0.1 liter, and 0.0010 liter containers using both the ideal gas equation and the van der Waals equation. So I don't know how you would find a container that is such a small volume. I'm guessing they compress a container to such volumes. You can definitely do that. So it's kind of like that picture we saw with the compressed gas containers here. You would compress a volume until the volume is very, very small, like right here. Okay. So first, let's do at 1 liter. So we have 1.0 liter container. Okay, so here's the 1.0 liter container. All right. So we know PV equals nRT. So let's calculate using the ideal gas law first. So if we solve for the pressure here, we get nRT over V. Okay, so let's plug in everything. 1.00 mole. R, so let's just keep the R constant right there. We are very familiar with the R constant by now, 0.08206, and the units there. So 0 degrees is 273. 0.15 Kelvin, so let's just use 0.15, and then divided by 1.0 liter. Okay, so we solve this. It's just going to be, well, not just that, but 273.15 times 0.08206. Okay, so we get approximately 22. So let's just keep a few extra digits here. 22. Actually, we don't have to. So we get 22, about 22.4 liters. But if we're rounding to sig figs, right, it'll probably be just 22 liters. Okay. Okay, so that makes sense, right? That's a volume of gas at standard temperatures and pressures occupies, well, not, I guess that wouldn't be being occupied there, but, so yeah, at 0 degrees, in a 1 liter container, it's pretty high there. So the pressure's pretty high there. Okay. All right. So if we use the van der Waals equation now, okay. So let's use the van der Waals equation. All right, for number 1. So we have P plus A squared, AN squared over V squared, right? Times volume minus NB. Okay, equals nRT. Okay, so we solve for this, right? First we divide everything by V minus NB, so we get P plus AN squared over V squared equals nRT divided by V squared. Okay, so I divided, oh sorry, not V squared, but V, not this, but V minus NB. Okay? Okay, so now we can then subtract both sides from this equation. Just isolate P here, and we get nRT over V minus NB minus AN squared over V squared. Okay, so it looks pretty complicated. But if we just plug in everything, it'll be okay. All right, so now we say P equals, so N is 1 still, so 1.00, R 273.15, and then we divide this by the volume here, 1.0 liters minus 1.00 times B. So let's go back to our chart here. Our value for B for oxygen is going to be 0.03803. 0.0, so 0.03803 here. Okay, so don't worry. Let's not worry about the units because they should cancel. It will be liter per mole. In this case, so that will cancel out the excess moles there. Yeah, okay. And then we subtract the A value. So the A value here is going to be 1.360. 1.360 times 1.00 mole squared over the volume squared, which is 1.0 liters squared. Okay, so I put some units, so maybe we don't have to put the units because we will just assume they all cancel, okay? So let's just assume they all cancel. Okay, so if we do that, we do get, I believe, so let's just do this calculation together here. So the top of the fraction in the first on the first fraction here, it's going to just be 22.4, right? Because we did that before in the previous example, 22.4, the top of the fraction. Then we divided by 1.0 minus 0.03803. Okay, so there we get, so the first fraction is approximately, okay, and then we just subtract this number by 1.360, right? Because 1 squared is still 1, and divided by 1 squared is 1, so it's just going to be minus 1.360. Okay, so we get a pressure of 21.9 liters. Okay, so right here, normal volumes. The pressure predicted from the ideal gas law and the van der Waals equation looks pretty good. So it's 21.9. So that is all right. So that's pretty good. That's in pretty good agreement. So that's the 1 liter container. Okay. So now let's now go to the second example. So let's go to 0.10 liters. Okay. So let's erase all of this. We could just erase the values here. We don't have to actually erase everything. So actually this should stay the same, right? What changes here is the volumes. So let's just erase this one. That will stay the same, and then that will stay the same, but the volumes here are going to change here, right? So the only thing that changes really is the volume. Okay. All right. So first, let's do the 0.10 container. Okay. So actually, so that one we said was 21. We said at first it was 21.9 ATM, right? Well, we should probably round it to 22. So it actually predicts it pretty well. So 22 ATM. Sorry, 22. Wait, why is this liters? Sorry, this should be ATMs. My apologies. So the pressures are predicted pretty well at regular temperature and pressures, right? So that's pretty good. But we're going to see now what happens when we decrease the volume. Okay. So in this case, we're going to change the volume here to 0.10. Okay. So when we do that, right? When we do that, we get 0.08206 times 273.15. Now we do that, our pressure here is going to increase by a factor of 10, right? Yeah, so it's going to increase to a factor of 10 or 224. 24.15 ATM. But in sig figs, we were around just 220 ATM. Okay. So now if we put in our values here, 0.10 and then 0.10 liters squared in our equation here, we'll see that they should change dramatically. Okay, so let's do 224.15 divided by 0.1 minus 0.03803. Okay. Okay. So, and now if we now we take the sum of that value here and subtract it by 1.360 divided by 0.10 squared, we get a very interesting number, to say the least. Okay. Yeah, so it's 0.1 minus 0.03803 minus 1.360, 1.00 squared divided by 0.1 squared. Okay. Let me just put this in my calculator, but different here. Yeah, so we get 3,481 atmospheres. So this rounds to 3,500 ATM. So see, there is a big discrepancy here between what it should be possible, we should expect, and what we actually get. So we actually get something really large. So in here, the ideal gas law would fail. Okay, but let me just double check here. Because I want to make sure I got the numbers right. So let's see here. Okay, this is chapter 5, right? Yeah. Okay, so oh wait, what's wrong chapter here? Okay. Maybe I did something wrong, because it should have came out a bit differently. Huh. Did I do it right? and RT. Okay. Okay. Maybe I did something wrong here. Because the number I got is a little bit off. Okay. Let's see here. So let's check our calculation again. Okay. So, oh, maybe I didn't do 220. What? Yeah, I did 220 though. Let's see. Oh, wait, sorry. No, it shouldn't be 220. I did something wrong. So I calculated the first fraction incorrect. So let's just change that back here. So it's actually 22. Okay. So yeah, it should actually be 220. Or in this case, 22.4. Yeah, so it should be it's a little off there. Okay, so it's roughly 2.3, so 225. This 8.5 atmospheres, but we would round this to 230 atmospheres for 2 sig figs here. So you see here, it's still a pretty good agreement. 220, 230. So that's pretty good. Okay. But let me just double check something here. I wanted to do something here. Let me just double check the first example we went over. Just because I think the value's a little bit off. Okay. Interesting. 22. Oh, interesting. They got a different value. Okay. No, I think we're good. Yeah, we're good. The value's just a little bit off, but it's okay. All right. So you see here, still at 0.1 liters, the volumes are still pretty good according to the real gas law and the ideal gas law equations. So that's good. Now let's go even further. We're going to decrease the volume 100 more times, 100-fold. So let's see how that pans out here. So the only thing we're changing is the volume units here. So now we're going to go to 0.0010 liter. Oh, okay. I think I wrote this a little bit incorrectly. I think I meant to write 0.010 liters. Yeah, I think that's what I was supposed to write. Okay. Yeah. So that's really small, and it doesn't really match up with our volumes here. So let's just correct that right here. So we're going to cross that out and write 0.010 liters. Sorry about that. I was supposed to fix that. But no biggie. Now let's go over into our calculation here. Okay, so now the volumes will be even smaller. So a factor of 10, not 100, sorry. 0.010 and then 0.010 here. Okay. So now let's plug that into our calculator. So in this case, it'll be, okay. So first, let's calculate the ideal gas law, the pressure from the ideal gas law. Okay. So 0, oops. Okay. So in this case, it'll be 273.15 times 1 times 0.08206. Okay, so we have our first, the numerator, and then we're going to divide 0.010, which is just going to increase our pressure now by a factor of 10. So we get 2,241 atmospheres. So that's a big number. So we could just round this to 2.2 times 10 to the third atmospheres. Okay, there we go. All right. So okay, yeah. All right. So so in this case, now we can plug in this value in to our real gas law equation, the van der Waal equation. So let's do that right now. So we get 2,241. Well, we could just keep 2,200, but I'm just going to keep some extra digits here, just so we don't have rounding error. All right, divided by 0.010 minus 0.03803 because we only have 1 mole, so it's going to be multiplied by 1. Okay. All right, and then when we do that, let's put in your calculator. You want to make sure you put some parentheses, or you could just calculate the values intermediately in the middle, and then just use those values carry on to your calculation. But it might be better to just put all the whole calculation all at once in your calculator using parentheses. Okay, so minus 1.360 divided by 0.010 squared. Okay. Now I think I did something wrong because the value here is very weird. Okay, this one. Huh, okay. 0.3803. So 0.010. Okay, minus 1.360. Interesting. I'm pretty sure I got this correct. Okay. Let me just troubleshoot a little bit here. Okay. So 1. Ah, crap. I keep doing the same mistake. Okay. Sorry, everyone. So it should be. I keep doing the same mistake here. That's why I keep getting confused. I'm trying to take little shortcuts. So don't do shortcuts, everyone. Okay. All right. So the pressure here, since you think it's a very small number, we're going to get a negative number actually. So it's going to be negative 14,399 So look at this, round this to 400 actually. So it fails. The calculation fails. A negative pressure results, but we know pressure is either 0 or above 0, so it fails. So in this case, this is where we can't really use the ideal gas law to represent the behavior of oxygen gas at such a low volume. So this is where the calculation fails. So we get negative 1.4 times 10 to the 1, 2, 3, 4 times 10 to the 4th pressure. So this does not work. So calculation fails. So you see here, the ideal gas law is not a good model at very low pressures. Sorry, not very low pressures, very small pressure. So this is where the calculation would fail in this regard. Okay, so that is it for chapter 5, and next lecture we will start thermochemistry. So we'll start talking about how chemistry and energy are related and how chemical reactions generate and transfer energy can be used as a source of heat storage or energy transfer. So I'll see everyone in the next lecture. All right. Take care.